Okay, great. So let's start. So welcome to the Israel Algorithmic Game Theory talk. Today we'll have Yoav talking about optimal collaterals in multi-enterprise investment network. So welcome, Yoav.
Thanks, Moshe, and thanks for having me. And Moshe already presented the title, Optimal Collaterals in Multi-Enterprise Investment Networks. And this is, in fact, a joint work with Moshe and with Eyal Winter. And we'll be talking about settings where there are firms that try to raise capital from investors. And these investors face strategic risk, meaning that their losses or their profits may depend on actions of other investors. And we'll talk about collaterals as a mechanism design tool to incentivize investors to invest. And we'll also talk about investment networks, which we will present later. So let's start from an example. Let's say that we have a firm that tries to raise capital for some enterprise. And this firm needs to raise at least $4 million to cover the costs of this enterprise, for this enterprise to be completed. And the enterprise promises returns to investors, and the returns are going to be the total invested amount minus the cost of 4 million. And this is going to be multiplied by 2 in our example, which is some interest. And this is if the cost is covered. If the cost of the enterprise is not covered by the investments, then the returns are going to be just 0. There will be no returns. And this total return will be divided between the investors proportionally to their investment amounts. And now let's say that Alice, Bob, and Carol, they represent firms and they consider investment opportunities in that enterprise. And in the drawing here, the arrows point in the direction of the returns. A little bit confusing, but they point towards the investors. And each one of them considers an investment of amount $3 million. And this is going to be a one-shot game in which every investor needs to decide whether to invest, and we'll call this strategy cooperate, or not to invest, and we'll call this strategy defect. And let's look at some investment scenarios, what can happen in this game. Let's look from the viewpoint of Alice. If only Alice invests, then the total investment is going to be $3 million. And this doesn't cover the cost of $4 million. And therefore, the returns are going to be 0. And in this case, Alice would prefer to defect because she invested $3 million and lost them, didn't get any return. A second scenario, Alice and Bob invest, but Carol defects. So here, the total invested amount is $6 million. And therefore, the total return will be 6 million minus the cost of 4 million multiplied by 2, which gives us $4 million. And the return to Alice is going to be $2 million because the total return is split between the two investors. And again, Alice would prefer to defect in this case because she invested 3 million and got back only 2 million. And the next scenario, all the investors decide to invest. So they choose a strategy cooperate, choose to invest. And then the total investment amount is going to be $9 million. The total return will be 9 million minus 4 million cost multiplied by 2, which gives us $10 million. And this is split between the investors, between the 3 investors. So the return to Alice is going to be $3 million and 1/3. $3 million and 1/3 dollars. So in this case, Alice has profits and she prefers to cooperate, to invest.
Yoav, it seems like there is a question by Yuval. So,
yeah.
Yes.
Hi. Just a quick question to make sure I understand. Throughout this whole talk, we only regard like either all or nothing investment?
Yeah, it's a good question. We regard, yes, first answer is yes. And also can think about it that if Alice would prefer to invest only part of her amount, it means that she has profit. And if you look at how this total return looks like, if she has profits for investing 2 million, then she would prefer to invest the whole 3 million in this example. But the answer is yes. We consider take it or leave it investment opportunity. Okay. So a few observations about the example. First, we saw that indeed there's a game between the investors. And we can also see that all cooperate, the strategy profile where all the investors decide to invest, is a Nash equilibrium of this game. And we see this because when everyone invests, everyone has profits. So none of them would like to deviate from this strategy profile. And this outcome is efficient. Everyone has profits. The cost of the enterprise is fully paid. So this is good. But we can also see that all defects, the strategy profile where none of the investors decide to invest, is also a Nash equilibrium. And we saw this because when Alice invested alone, then she didn't get any returns, so she prefers to not to invest. So all defect is also a Nash equilibrium. And so we have a good equilibrium and a bad equilibrium. And we can ask how to induce a unique equilibrium of full investment, where all the investors decide to invest. And we'll see how collaterals can help with this. And for this, we need to define how the collaterals are going to work. So a collateral is given for an investor for a specific investment, and it provides a limited amount insurance for the invested amount for this investor. So if there are profits, if the return is more than the invested amount, then the collateral is not realized, and the investor just gets the returns from the enterprise when there are profits. And if there are losses, meaning that the return is less than the invested amount, then the payoff for an investor that has a collateral of amount C is going to be the return, whatever he got as a return from the enterprise, plus the collateral, but this is going to be kept at the invested amount because the collateral is only an insurance for the losses from the invested amount. So this is how the collaterals will be defined. And let's return to our example and see exactly how they work in the same example where Alice now has a collateral of $500,000, just to make sure that we know what happens with these collaterals. So in the first scenario, only Alice invests. We said the total investment is less than the cost of the enterprise, and there are no returns. So the utility for Alice is going to be $500,000, which comes only from the collateral. There are no returns. Second scenario, Alice and Bob invest, and the total investment is $6 million. And we saw before that the return is going to be $2 million. So the utility for Alice is going to be $2.5 million. In this case, $2 million from the return, $500,000 from the collateral. And in the case where everyone invests, in this case, we saw that there are going to be profits for Alice. Therefore, the collateral doesn't kick in. So actually, the utility for Alice is only from the return from the enterprise, because the return is more than the invested amount. And one last scenario, let's say now that Alice and Bob are going to invest, but now Alice has a larger collateral of $2 million. So what will happen then? The utility for Alice is going to be $3 million, which is $2 million returned from the enterprise, plus only $1 million from the collateral, because the collateral is only an insurance for the losses. So it covers only up to the invested amount, if it can. Okay, so this is how the collaterals work, and let's see what we can do with them. Can we induce a unique equilibrium of full investment using this type of collaterals? And let's consider the following collaterals. Let's say that Alice has a collateral of $3 million And we call this a full collateral because it covers the full investment amount that Alice has. And Bob has a collateral of $1 million. And we call this a partial collateral because it covers only a part of the investment amount. And Carol doesn't get any collateral, or we call this a zero collateral. And let's see what happens in the game with these collaterals. So Alice now has a dominant strategy to cooperate with the full collateral because she can only gain from cooperating. And Bob knows that Alice will prefer to cooperate. And Bob also knows that if only he and Alice invest, then the return from the enterprise is going to be $2 million. But Bob also has this collateral of amount 1 million, which means that the utility for Bob from cooperating is going to be at least $3 million. So if he cooperates, he will get at least the investment amount. And therefore, Bob also cooperates. And now Carol, that doesn't have any collateral at all, and knows that Alice and Bob are going to cooperate. And so Carol also cooperates without any collateral. And these collaterals induce a unique equilibrium where all the players choose to cooperate. And the total collateral here is 4 million, which is 3 million full collateral to Alice and 1 million partial collateral to Bob. And we don't need to give anything to Carol. And the question we're going to ask is, how can we find the minimum sum collaterals that induce a unique equilibrium where everyone chooses to invest?
Seems like we have another question.
Yeah.
Hi, sorry, just to make sure, but still, if everyone defects, it's still a Nash equilibrium, unless I'm missing something. I follow the logic that it makes sense that Alice would invest, and so Bob should invest, and that Carol should invest. But the all defect will always, it seems to me that it will always be in this scenario, it will always be also a Nash equilibrium, a bit of a redundant one, maybe.
Okay, let's make sure I understand the question. If
everyone defecting
full...
is not an equilibrium.
What?
Everyone defecting is not an equilibrium. That's the answer.
It's not an equilibrium because Alice has a full collateral and she prefers to cooperate, even if she cooperates alone.
She gains nothing, right? Like gets zero if she
yeah, okay. So we can assume, to make things much simpler, we can assume that there is a tie breaking towards investing in case of equal utilities. Some good motivation for this is that I think good motivation for this is that if Alice cooperates, she will get at least 3 million. She can get more. If Alice defects, she will just keep the 3 million. There is no
I guess you can also just think about increasing it by epsilon.
Yeah,
yeah, exactly.
A little bit.
That's how you formalize the assumption of tie breaking, right? Thanks. So either you look at the motivation of best case profits versus worst case profits, or you just add epsilon to the utility from cooperating, which also works. So we assume that there are no ties here. Okay, and we'll be talking about cases where there can be many investors. And then we need to figure out how to define and solve an optimization problem for these collaterals to induce this unique equilibrium. And we'll also talk about cases where there is a network of investments. Some of the investors may actually be firms that have their own enterprises, and they're trying to raise capital for their own enterprises. And they need to pay the costs of these enterprises. And so some of the investors may actually reach a state of default, and then they will be unable to invest, even if they have the incentive to do so. And this adds more considerations to the players, which they need to think about. And we will see results about different network structures and how they affect the problem we just talked about. Okay, so this was the example. And Next, we're going to present the model of this game a bit more formally, exactly the same game as we saw in the example. And then we'll formally define the problem, see some characterization, basic characterizations of this game. And then we'll continue to talk about results in different types of networks. So we'll start from a few notations. V is going to be the set of firms. Each firm can consider investments in enterprises of other firms, and it may have its own enterprise and be raising capital for its own enterprise. And G is going to be the investment network, the graph, where the vertices are V, the firms, and an edge pointing from K to I means that firm I considers an investment in the enterprise of firm K. So again, the arrows are directed in the direction of the returns. They're pointing towards the investors. And this graph is going to be weighted, and the weights for the edges will be the amounts of the investment opportunities. We denote them by XKI, which is the investment opportunity of I in enterprise K. ZK will be the cost of enterprise K. Alpha K will be the interest of enterprise K. And we consider this investment network as a given input for the problem. Okay. Now, like we saw in the example, if some firm I has an investment opportunity in enterprise K, this firm needs to decide whether to invest, which we call cooperate, or to decline the investment, which we call defect. And we denote by DK and CK the sets of defectors and cooperators in enterprise K. And a defector just keeps the investment amount, like we saw in the example. Doesn't make this investment. And now some firms may reach a state of default, which we'll see about more in the next slide. And a firm in default can't actually carry out the investment, even if it wants to invest. And we denote by IK the investors in enterprise K. Those are the firms that decided to invest and are actually able to invest. And how does a firm reach its default? If a firm has an enterprise and it didn't manage to raise sufficient investments to cover the cost, then this firm will be in default. And a defaulted firm just cancels all its investments, and we assume zero recovery. So the cost of being in default is very high. And the set of investors, those firms, those players that actually can manage to invest, decided to invest and are able to invest, is induced by the strategy profile of all the players in the network, and it can be uniquely determined. It is uniquely determined. If we know who decided to cooperate in which enterprise, we can tell you who are the firms in default and who will be the set of investors for each enterprise. Okay, so I won't get into the specific process. And if some enterprise, let's say that it's not in default. So this enterprise has enough investments to cover the cost and perhaps more. And so the remaining, the net amount, which is the total capital raised minus the cost, has interest alpha. And the return to investor I from enterprise K is going to be, let's look on the left term here, it's going to be the proportional share of the net return. So we'll see how this looks like. This is the total invested amount. Z is the cost. And this will be multiplied by 1 plus interest, which in the example was 2. So we had in the example, we had an interest of 1. And the term on the right is just the proportional share of investor I among the investors in enterprise K. So this is how the returns look like. And we'll define the collaterals. And again, it's like the collaterals we spoke about earlier. A collateral is given per investment. Collateral CKI is for investment XKI. And if the return is less than the invested amount, then the collateral can be realized, and the utility for a player that has a collateral will be the return. Utility of I will be the return from enterprise K plus the collateral given for this investment, but kept at the amount of the investment. And if there are profits, then the collateral is not realized. And this is important because the solution concept we are interested in is a unique equilibrium where everyone chooses to invest. And notice that in this here on the equilibrium path, the collaterals are not realized. And we denote by C a matrix of collaterals just holds the collaterals for all the players, and those investments that do not exist in the network where XKI is 0, then we define the collateral to be 0, just technical. And so the utility from enterprise K for a player that decided to defect will be just keeping the investment amount, XKI. The utility from cooperating but being in default will be 0. And the utility from investing when there is a collateral CKI will be the return from the enterprise if there are profits. If there are losses, but the collateral can cover these losses, then the utility will be the investment amount. And if there are losses and the collateral can't cover them, then the utility will be the sum of the collateral and the return from the enterprise. The total utility of a player is the sum of utilities from all the investments that this player considers. And this defines, this model defines a simultaneous move, full information game. And the game is induced by the input, which is the investment network, and the collateral metrics. Okay, so now let me remind you, our goal is to reach a unique equilibrium where all the players choose to invest. And some remark about this, we consider only those enterprises that are potentially profitable. If everyone invests, there will be profits from these enterprises. And this is because if we have an enterprise that even if everyone invests, it's not profitable, then there is no point giving collaterals here. It's efficient, and we just remove these enterprises from our network. We consider only profitable enterprises. And also, it's useful to give a name to this property that we are looking for. So if some collateral metrics manages to induce a unique equilibrium of full investment, we call this a viable collateral matrix. And the collateral minimization problem asks, given input of an investment network, to find the viable collateral matrix with minimum total collateral, the minimum sum of collaterals.
Yoav, can I ask a question?
Yeah, sure.
Is there any private information here, or is it a full information game?
Full information, yeah, definitely.
So in what sense do you call it a mechanism design problem? Isn't it just an algorithmic problem?
I think the idea is that we can induce different games, and collaterals are in fact a commitment that that is being taken before the game starts. So I think in this sense, it is a mechanism design problem.
Okay, but we can think about it as an algorithmic problem. We have the network structures with all the input, and we need to find the optimal collateral vector to induce Okay. Yeah. I mean,
Yes,
it's totally fine. It's totally fine to call it. It's fine. I just wanted to make sure I understand the setting.
Well, I'm not sure I understand the subtlety here, but I think perhaps you could call it an algorithmic problem because there is an you can try to solve it.
Michal is alluding to terminology which is correct. I mean, usually when we talk about mechanism design, we talk about eliciting preferences. But I think the term contract theory is different in the sense that you design a game to get some outcome. Okay, so maybe we have to term things in terms of contract theory rather than mechanism design.
Okay, thanks Eyal for that clarification. And the other question, you say that you consider only sub-networks of profitable enterprises. Mm-hmm. Is it equivalent to just assume without loss of generality that all your enterprises are profitable?
Yes. You can assume that. So yes, that's exactly what I mean.
Okay.
You can assume that all the enterprises are profitable.
Okay.
This is the assumption that we make, right?
Mm-hmm.
Thank you.
Yes, maybe the way it's written is to show the motivation, but I guess it's clearer to just say that this is the assumption. That's right.
Okay, great. Thanks.
Okay, so this is the problem that we consider. And now let's look at some basic properties of this game. And the first property is shown in this result. It says that if the game induced by the collateral matrix has a unique equilibrium where all the players choose the strategy cooperate in all their investments, then the game is dominant solvable, meaning that we can reach this unique equilibrium through a series of iterated elimination of dominated strategies. And as we said before, we break ties towards investing, so it's all strictly dominated strategy. We don't have ties here. And the idea of the proof is first to assume, okay, so let's assume that the collateral matrix does induce a unique equilibrium of full cooperation. This means that the strategy profile where all the players defect, this can't be a Nash equilibrium because we said we have only one equilibrium. And this means that there must be some player who prefers to cooperate even when all the others defect. We'll call this player I1. And now, another thing we know is that the utility for I1 can only increase if more people will cooperate. And then we can say the following. The strategy profile where everyone defects and I1 cooperates, this also can't be a Nash equilibrium. This means that there must be another player, which we can call I2, which also prefers to cooperate if only I1 cooperates. And he will also prefer to cooperate if more players will join in and cooperate with them, because the utility can only increase. And this argument goes all the way down to the last player. So in fact, we show that if we assume this unique equilibrium, the game must be dominant solvable. And this property is quite useful because once we know that there is a sequence of iterated elimination leading to the unique equilibrium, this can help us to construct a solution for the collaterals. So the previous result told us that if the collateral matrix induces a unique equilibrium, then it's dominant solvable. But can we always find such a collateral matrix? And we show that in fact there are networks where you can't induce a unique equilibrium with collaterals. There are networks where a solution doesn't exist. And we show that for a given input, solvability of this input can be determined in polynomial time. And the intuition here is that you can use full collaterals. And if you give full collaterals and you don't manage to find any iterated elimination leading to the unique equilibrium, if full collaterals didn't help you, then nothing will help you. So basically, this is the intuition. And we also show that those problematic networks that you can't solve must have a very specific type of cycles. And this means also that characterization shows also that in acyclic networks, a solution always exists. We can always find collaterals that induce a unique equilibrium of full investment if the network is acyclic.
May I ask two quick questions? First of all, if we give everyone a collateral equals to their investment amount, wouldn't it be a Nash equilibrium where everyone has an incentive to invest?
Yes, good. Yes, exactly. That's what you just described, is giving full collaterals to all the players. So this is this is true. The intuition for showing how to determine if some instance is solvable or not is exactly to give full collaterals, and we show a constructive process how to do this, and even how to identify the problematic parts in the network. But I won't get into these details now.
So, I think Yoav's question was how come giving full collateral is not always inducing a
Nash equilibrium
of full cooperation. Is this right?
Oh, so,
yeah.
Yeah, okay, so we'll see an example.
One quick question. If I'm also getting investments and also invests by myself, it doesn't counter each other, right? If I need to reach a capital of ZI, if I invest a certain amount, it doesn't come out from this ZI.
No,
right?
no, you
two separate
this,
questions. I have two entities. One entity which is my investment entity, and one entity is my asking for investment.
Yes, that's a good way to put it. It's you have this firm has its enterprise, so its enterprise has a limited liability, so its relations are with the investors. This firm also invests in.
Okay.
The problem comes if a firm enters a state of default, so it can't make investments.
Mm-hmm.
Yeah, the default is actually linking these two entities, right? Like you cannot invest if you're in a default.
Yes, exactly. Okay, so
it does sort of come out from this Z, the required ZI. So okay, I'll say it later. Sorry.
If the investment default happens if the total invested amount for a firm that has an enterprise does not cover the cost. This means that this firm will be in debts and it will be in a state of default. And but I think the way you put it is correct. The investment entity and the
Thanks.
Yeah. Okay, so next we're going to see some results for very simple networks, networks with only one firm that raises capital. And this is similar to the example we saw at the beginning. And then we'll continue to more complex networks. So the single enterprise problem, or the star graph problem, if you wish, we have one firm here in the middle that has an enterprise with cost Z and interest rate alpha, and we have n players. So we're not counting this firm in the middle as a player, because in this network, this firm in the middle doesn't make any decision in the game. And we don't have any cycles in this network, so we know that the solution must exist. For example, if you give full collaterals, they should work. They're not optimal, but they can work. And we can ask how to find the optimal collaterals, how to solve this problem. And a result we show on star networks says the following. If we know about a subset A of players that have full collaterals, collateral equals the investment amount, in some optimal solution, the theorem tells us that this is enough and we are able to calculate the collaterals to all the players. We can calculate the optimal collaterals for all the players if we know only the subset of players that have full collaterals in this solution. And so this tells us that an optimal solution can be specified by the set of full collateral players, and you can think about the problem for the star network as how to select this subset of players. And also the theorem shows that the partial collaterals, these collaterals that are not full collaterals, they are not proportional, but they are increasing, the collateral amount is increasing with the investment amount. So the larger investors get higher collaterals, both in percentages and in total, in absolute value. And another result we show on the single enterprise problem is that it's NP-hard. So if we have a large number of investors, it's going to be hard to solve this problem. And the idea of the proof is, first we show that if the interest rate is high, then all the collaterals must be either full collaterals or zero. We don't have partial collaterals. And this allows us to do a reduction from knapsack. And what are the implications for networks? Of course, this means that the problem will be hard for networks as well. So every network contains a star subgraphs in it. But we can think about a setting where the network can be very large, can be unbounded, the number of firms, but the number of investors per enterprise in each enterprise is going to be bounded. And in such a setting, then this hardness result will not necessarily be problematic. And we can think about what happens in networks, even in large networks. Questions about these results? Okay. So now let's continue to discuss more complex networks. And in a network environment, as we said, things are more complicated. The players need to consider also the possibility that some investors will be in default. So we're going to construct an example that demonstrates this. So here we have a star network, only one firm that has an enterprise and 3 investors. And each investor has an investment amount of 9, and the cost is 20. So to cover the cost, it's required that all the investors, all 3 investors will invest. If only 2 invest, total investment is only 18. So if not all the 3 players invest, if one of them defects, then the firm will be in default. Firm number 0 here will be default. And we can duplicate this star network to create a chain. And all the stars in this chain are exactly with the same parameters. And let's see what happens if one of the investors of firm number 6 decides not to cooperate. So what will happen? If one of the investors defects, then firm number 6 will reach a state of default because it doesn't cover the cost. But if firm 6 is in default, then firm 6 can't carry out the investment in the enterprise of firm number 5. And this means that firm number 5 will also reach default. And then firm number 5 can invest in 4, and so on. And we have a cascade of defaults that in fact covers all the enterprises in this network. So in this example, those investors here, A and B, need to consider not only whether investor 1 will want to invest, they also need to consider whether investor 1 will be able to invest. And in fact, in this example, they need to consider the strategies of all the players in the network to make their decision. So this network structure adds more risk to the players the investment has an additional source of risk. And this is something that the players will need to think about. And we are asking first how to solve the problem for acyclic networks. And also, does this additional risk that we have in the network environment lead to higher collateral that we will need to give to the investors? Will the collateral will be more expensive or higher collaterals? And to compare the network environment to a non-network environment, we use a definition of a star decomposition. And I'll show this definition with an example. Let's say that we have this network, network G, and this network has three enterprise vertices, firms that have their own enterprises, 1, 2, and 3. And again, the arrows point towards the investor. And the star decomposition going to look like this. What the star decomposition does, it takes every firm has its own enterprise and its potential investors and considers them as an independent star network. And the star decomposition is going to be just the collection of these star networks. Now notice that the vertices in the star decomposition can appear more than once, but the edges are the same as in the original network. And each edge represents an investment, some investment decision that someone needs to make. So the star decomposition preserves exactly the same investment opportunities as in the original network. And the result we show about acyclic networks says the following. If you want to solve the collateral minimization problem, to induce a unique equilibrium of full investment with the minimum sum of collaterals for some acyclic network, what you can do, you can look at the star decomposition, solve the problem over the star decomposition, which is a collection of star network problems. And then those same collaterals will be optimal also for the network itself. And the idea of the proof, first, we say that the optimal collaterals in the network can't be any less than the optimal collaterals in the star decomposition. Or otherwise, we could give less also in the star decomposition, which can't be because we said it's optimal. And then a proof shows how to construct an order of elimination, of iterated elimination of dominated strategies that leads to the full investment equilibrium. And the idea here is that in an acyclic networks, you can always find some enterprise whose investors are not worried about defaults. Because they are in the periphery of the network. So they are high in the topological order of this network. So if you just make sure to give collaterals to these players first, then you remove the risk that this firm, here firm number 3 will be the first one that we need to deal with. You remove the risk that firm number 3 will be in default, and then you can continue on down the order, down the topological order of the network. Basically, this is the idea. And again, what this means is that you can, to solve the problem for the network, you just need to solve the problem for the star decomposition, for the non-network environment. Okay, so let's summarize what we saw about acyclic networks. So first, we saw that in acyclic networks, a solution always exists. You can always find collaterals to solve the problem. And we can also know that for acyclic networks with a bounded degree, the number of investors per enterprise is bounded, then the problem can be solved in polynomial time. And this is because if we can solve every star network in a constant time, because the degree is bounded, we have only a polynomial number of star networks. And so the solution will be polynomial time. And even if we want to find specifically the order of elimination, so also finding the topological ordering is also polynomial. So we can specify the full solution for bounded degree acyclic networks in polynomial time. And also, conceptually, a globally optimal solution for the network is obtained by the collection of local solutions. In other words, firms can actually ignore the network. Each firm can mind its own business and consider its own investments, and each firm that has an enterprise can optimize its own collaterals, and this is going to work and be optimal.
Yeah, can I ask a question?
Yeah.
So in the general case, if you don't have a bounded degree network, and suppose we are in the acyclic case, so the computational complexity is like knapsack, like do you have a pseudo polynomial algorithm and FPTAs and all that, or is it harder?
Good question. I'm not sure if it's harder. My hunch is that it is, but I'm definitely not sure. Finding a dynamic programming solution for this is not as, we didn't manage to do that yet.
I think it sounds promising to me. I think, the problem is to determine the order of elimination, right? Like the order of the chain. Once you have the order, I think you just, it's trivial, right?
Once you have the order, then yes, we can calculate. If you have the order, we can calculate the collaterals, right?
But you have n factorial orders. That's a lot.
No, the order is not enough. You also need to decide who will get full collateral.
No, if you know the optimal order, if you know the optimal order, this is correct. You can, if you know the optimal order, you can just do the calculation.
Right.
And it's in a closed formula, so that's not the hard part. The hard part is that you have this a factorial number of, but even for the star network, then which is what we need to do for the NP hardness result, the problem doesn't look exactly like knapsack. For the reduction, we needed to take a high interest rate to turn it to look exactly like knapsack. So it's a special case of our problem that it looks like knapsack. But when you have those partial collaterals, you have this strange mixture of trying to optimize this packing problem for the full collateral players and also the collaterals, the partial collaterals to the other players. So maybe it may be that you can find an FPTAs, but it's not very simple to do so, at least. This is what I can say about this, I think.
Thank you.
Yeah. About the third result, about the acyclic graphs. So we say that the sum of the optimal collaterals is the same as in the star decomposition, but the collaterals themselves aren't. Like I can't use the same matrix.
They are exact. Well, first need to keep in mind that a solution is not necessarily unique. So need to be careful about saying those are the optimal collaterals, but because there may be several solutions, but the optimal collaterals of the star decomposition or an optimal collateral solution for the star decomposition will be optimal also for the network. The exact same collaterals will work. But I wrote here the sum because the total collateral is what we are interested in. If we can play with the collateral somewhere and reduce the sum, so we'd like to do that. So the sum is what's really interesting to minimize.
And can we say something interesting about the sum? Like, can we bound the sum? Like, identify when we need full collaterals and when we only need partial ones, etc.
Yeah, we have some characterizations, but it's rather technical about when would a player need a full collateral and when would a player will not need any collateral. And so, yes, you can say some things about that. But I think the interesting part here is that in an acyclic network that can still have a complex structure, in fact, everyone can ignore the network. I think that's the main takeaway from this result. So if everyone ignores the network and mind their own business, then it will be optimal also for the entire network. So you don't need some central designer to do anything here.
Is it correct to say that this is because the problem isn't whether investors want to invest, but rather whether they are able to invest because of states of default? Like, as long as everyone is able to invest, then it's like the star decomposition, they can ignore the network. And worst case,
yes,
they are
exactly. If you do, actually, if everyone wants to invest, then we just show explicitly that an order of elimination exists. You can find it. It exists and you can find it. Yes. This answer the question? Or?
Yeah, thanks.
Okay. Okay, so this takes us to cyclic networks. So we saw that the total collateral in acyclic networks, the total collateral was the same as in the star decomposition. We can ask if this is true also generally. And in fact, we show that this is not correct. And following results says that you can find the cyclic networks where a solution exists, but the optimal solution, the total collateral will be much higher than this of the star decomposition. And we'll prove this with an example. Let's look at the following network. And this example is parameterized by one parameter, k greater than 2. Think about it as some large number. And we have 3 enterprise vertices, A, B, and C. And each one of them has a cost of k plus 1 and an interest of 2k. And this is the star decomposition. And what the theorem says is that we can find examples where the optimal collateral here in the network can be much higher than the optimal collateral in the star decomposition. So let's start from the star decomposition. And in the star decomposition, the optimal collateral that you can give, the minimum collateral you can give to induce a unique equilibrium is 6. 2 for each star problem. And the way this goes is you give a full collateral to A1 here, and a full collateral to investor B. And then A2 will invest also without a collateral. And why is that? It's because if there are already 2 investors that have a dominant strategy to invest, and A2 invests as well, then the total investment will be k plus 2, which is more than the cost. And we have a very high interest here. So there will be enough returns. So A2 will have profits. So the optimal collaterals in the star decomposition, the composition is 2 from each enterprise, which sums up to 6. And I argue that this is not going to work in the network itself. And why is that? It's because, let's try. If we give a full collateral to A1 and a full collateral to B, then A2 will not be able to invest, will not want to invest, because A2 can't be sure that investor B, that firm B is not in default. It may be the case that firm B will be in default, and then A2 will not have any returns. And therefore, what we need to do is to give a full collateral to A2 and a full collateral to A1. And then we know that firm A will not be in default because the cost of the enterprise is fully covered. And then we look on enterprise C and say the following: we give a full collateral to investor A, a full collateral to C1, and then C2 knows that firm A is not in default and has a full collateral. And he also knows that C1 has a full collateral. And so C2 will choose to invest. And the same goes also for enterprise B for this. And so the total, the optimal total collateral in the network is going to be k plus 5, which of course can be much higher than 6, depending on the parameter that we choose. And this shows us that local solutions are not sufficient anymore. The firms can no longer ignore network effects. And also, and this is in contrast to what we saw in the acyclic case. So here they can't ignore the network. And we also see a coordination problem that arises here because, okay, so we said that we need to give a full collateral to one of the large investors, but which one? So we don't want a situation where too much collateral is given, more than is necessary. So here, in fact, some central planning or coordination will be required, and this is different from the acyclic network case. And one more result about cyclic networks. We show that in cyclic networks, even if we have a way to solve the star problem, the single enterprise problems, still the collateral minimization problem is going to be NP-hard. And we show this with a reduction from the feedback vertex set problem. So in fact, in cyclic networks, even if the degree is bounded, then still the problem can be hard. Okay, and let's summarize about cyclic networks. So we saw that there are cyclic networks where we can't find any solution. And we also saw that there are some cyclic networks that are solvable, but the sum of collaterals can be much higher than the local solutions, the solutions on the star decomposition. And we also saw that cycles introduce further complexity, even for bounded degree networks. Okay, and let's conclude. So we studied the investments in networks. We defined and analyzed the collateral minimization problem, which by now I hope you all know is finding the minimum collaterals to induce a unique equilibrium where all the players choose to invest. And we saw results for a single enterprise that raises capital. First, the solution can be specified by this set of players who have full collaterals. And also we saw that the problem is NP-hard. And in acyclic networks, we saw that in fact, the firms can ignore the structure of the network. Each firm can optimize its own collaterals for its investors, and the investors will invest if they give the optimal collaterals. And specifically, there is no added collateral due to this structure of the network, which we could think that will happen because there is additional risk, but the same collateral as in the non-network environment works. And in cyclic networks, we saw that the solution does not always exist. There are networks that are not solvable. The cycles in the network can increase the total collateral that we need to give. And the cycles also add additional computational issues. And that's it. Thanks for listening. And happy to take questions.
Thanks, Yoav.